You just changed an entity field, ran the app, and immediately hit an illegal state exception. This is the Room schema mismatch crash. Room compares the expected schema hash, derived from your compiled entities, against the hash stored in the Room master table of the existing database file. If you modify an entity definition without incrementing the database version number in the database annotation, these hashes will not match. Room detects this inconsistency and terminates the application instantly to prevent data corruption. If you increment the version but fail to provide a corresponding migration object, Room throws a different exception, indicating a missing migration path. The fundamental rule is, any change to an entity, data access object, or view definition mandates incrementing the version number in the database annotation. Failure to do so guarantees an immediate runtime crash. Schema changes are implemented by extending the abstract Room migration class. This requires defining the specific start version and end version integers for the path being handled. The core logic resides within the migrate method, which receives a support SQLite database object. This object grants direct access to execute raw SQLite commands using the exec_SQL function. Crucially, Room automatically wraps all SQL operations within the migrate method inside a single transaction. This guarantees atomicity. Either the entire migration sequence succeeds completely, or it fails and rolls back, leaving the database untouched. Although wrapped in a transaction, migrations should ideally be written to be idempotent. Define the migration object as a constant, for example, using Kotlin, val migration _1_2 equals object :migration parenthesis 1, 2 parenthesis curly bracket . Curly bracket. Adding a new column is the most straightforward migration scenario, executed using the SQLite alter table add column command. If the new column is defined as not null in your entity, the alter table statement must explicitly include a default value. This default value is necessary to populate all existing rows, preventing immediate constraint violations upon execution. For instance, to add a non-nullable Boolean column named isActive, the command is database.exec_SQL parenthesis quote alter table users add column is _active integer not null default 1 quote parenthesis. Room does not validate the SQL syntax or semantics. The developer is entirely responsible for ensuring the SQL adheres to the SQLite dialect and all defined constraints. Once defined, the migration object must be passed to the database builder using room.databasebuilder.add migrations parenthesis migration _1_2 parenthesis. Renaming or dropping columns requires a complex, multi-step procedure because standard SQLite versions commonly deployed on Android lack direct support for alter table rename column or alter table drop column commands. The industry standard procedure involves creating a temporary table that reflects the new schema, copying the data, dropping the old table, and finally renaming the temporary table. The sequence is strictly defined. First, create table new users defining the desired schema, including the renamed column. Second, insert into new users select data from the old table, explicitly mapping the old column name to the new column name. Third, execute drop table users to remove the outdated structure. Fourth, execute alter table new users rename to users. This four-step sequence is mandatory for preserving data integrity while simultaneously transforming the schema structure. Modifying a primary key constraint or changing the data type of an existing column, such as converting an integer to text, mandates the exact same temporary table strategy used for renaming columns. SQLite's alter table command does not support direct modification of column types or primary key definitions after creation. When inserting data into the new table, SQLite type affinity rules apply. If the conversion is non-trivial or risks data truncation, explicit data conversion must be handled within the select statement during the data copy phase. Furthermore, if the new schema introduces stricter constraints, such as a unique index, the migration SQL must include specific logic to cleanse or deduplicate existing data before the insert into step. Failing to pre-process the data will result in constraint violation crashes during the migration execution. Room automatically chains migrations when a user updates an application from an older database version to the latest version, provided all intermediate migration paths are explicitly defined. If a user jumps, for example, from version 1 directly to version 4, Room executes M1 to M2, then M2 to M3, and finally M3 to M4 sequentially. All necessary migration objects must be supplied to the add_migrations method in the database builder. If any required intermediate path is omitted, such as M2 to M3, Room throws an exception, immediately halting database initialization. Developers must ensure that the SQL written in each migration step correctly accounts for the schema state after the preceding migration step has successfully completed its execution. Migration testing is mandatory to guarantee both data integrity and schema correctness across updates. Utilize the MigrationTestHelper class within instrumentation tests to verify your migration logic. The test setup requires exporting the schema JSON files by configuring room.schema location in your build configuration, and setting export schema equals true in the database annotation. The createDatabase method initializes the database to the specified starting version using the exported schema JSON file as the source of truth. Subsequently, the run migrations and validate method executes the defined migration path. It then verifies the resulting database schema against the latest expected schema, ensuring all existing data remains intact and fully accessible through the new entity definitions. The fallback to destructive migration method instructs Room to drop the entire database and recreate it if a required migration path is missing. This mechanism results in complete data loss and is only acceptable for non-critical, cached data that can be easily re-fetched. If user data must be preserved, this destructive fallback must be strictly avoided. For handling application downgrades, where a user installs an older application version, use fallback to destructive migration on downgrade. This specific fallback only triggers when the installed database version is higher than the version defined in the application code. It prevents crashes during version rollbacks while still incurring data loss for the downgraded version.